Are mass and weight the same thing? In class and before class, we've been kind of using these terms interchangeably, meaning that they are the same. But it turns out that actually mass and weight are two different things. They're similar, but they are not the same. Mass is a property of the object. It's a measurement of the object's inertia or resistance to change in motion. It's also a measurement of how much matter the object contains, literally how many atoms make up the object. Weight is the force acting on the object's mass. So weight is the force of gravity pulling down on the object's mass. Mass is a constant number, meaning that it will not change no matter what situation the object is in. Weight can change if the gravity changes or if the system is undergoing a sort of acceleration. So let's just make sure we have this concept between mass and weight. Mass is constant, weight depends on gravity. So let's say we have Hello Kitty and she's on Earth. Her mass is 50 kilograms and the gravity here on Earth, acceleration due to gravity, is 9.8 meters per second squared. So to find her weight, I would multiply these two numbers to get a weight of 490 newtons. Now let's say she transports herself to the moon. Would her mass change or would her weight change? Well, her mass is constant, so she's still going to have a mass of 50 kilograms, but this time the gravity is 1.6 meters per second squared. So her weight is actually going to be much less than it was on Earth. Her weight's going to be 80. What about if she's in space? What would happen to her mass? Well, mass is constant, so mass is still 50 kilos, but floating around in space, gravity is basically 0 meters per second squared, so that means her weight would essentially be 0. We call this phenomenon weightlessness. And so weightlessness means that you are basically falling according to the acceleration due to gravity, and you don't experience any weight force or any normal force pushing up on you. So, how we weigh ourselves normally. We normally step on a bathroom scale to figure out how much we weigh. And our weight is compressing a spring. So the reading on the scale actually measures how hard the scale is pushing up against us. So it's measuring a normal force, the scale reading. If I push down harder on the scale, I'm going to quote unquote weigh more. But if I am being lifted up, I'm going to weigh less. And that's because I'm not pushing against the spring as hard. So we experience this phenomena in what's called the elevator dilemma. So if I stand on a scale in an elevator, the scale reading might change. What do you think is going on? Why would that happen? Well, the elevator isn't always traveling at a constant speed. Sometimes it's accelerating, and therefore if it's accelerating, you're going to experience a net force that's going to cause you to either push down on the scale more or push up on the scale. Push down more or push down less, changing your scale reading. We call this your apparent weight. It is also possible to be in an elevator, quote unquote, that's falling in free fall, and you can experience weightlessness, like this puppy right here. So this puppy is on a space station, I believe, but you can also take these 0G flights where basically they fly up really high and then the engines cut out and you just fall in free fall and you're going to feel weightless. You also experience this on the ride shown here in the Tower of Terror where you're literally falling in free fall, and that's why your stomach kind of goes up. So let's talk about the elevator dilemma. We need to define a few things. The mass of the person is constant, so the force of the weight is also constant. That's not going to change. F of n is the force of the scale pushing up on the object. This is going to be the scale reading. F net and acceleration always point in the same direction. So we're going to use this idea in order to figure out, is the scale pushing up on me more or is the scale pushing up on me less than the weight force? So situation 1 is no acceleration. So I know that I have the weight force, which is represented by this red arrow right here. That's always going to be pointing down. If I have no acceleration, that means I have no net force. So there must be some force balancing out that weight. Well, that's going to be the upward force provided by the scale. In this case, they're going to be perfectly equal because my net force has to equal 0. Case 2 would be I'm traveling upward and I'm speeding up. We're also going to say that up is positive, down is negative. So if I'm traveling upward and speeding up, that means my acceleration must be pointing upward in a positive direction. So that means my net force must also be positive. I still have this negative weight force, so that means my scale needs to be pushing up on me more than my weight force. So the scale reading is actually going to make it seem like I'm heavier than what I actually am. So the scale reading will be greater than the actual weight. Sorry, this should be case 3. Traveling up and slowing down. If you are slowing down, that means your acceleration is pointing in the opposite direction of your motion. So if up is positive and I'm slowing down, that means acceleration is going to be negative, which means that the net force must also be negative. So what that means is that my weight force has to be bigger than my normal force in order to get that negative net force. So that means my scale reading will be less than my actual weight. And so you're going to feel lighter than you actually are. Case 3, traveling down and speeding up. So again, if I'm traveling downwards, I'm traveling in a negative direction. And if I'm speeding up, the acceleration is going to point in the same direction. So acceleration must be negative. And so that means my net force must also be negative. So this case is very much like the previous case, where the scale reading is not going to be as big as the weight force. So I'm going to be weighing less than what I actually do weigh. And so that's why you kind of feel that initial like lift up when you're falling in the Tower of Terror. Case 4, traveling down and slowing down. So if I'm traveling down, I'm traveling in a negative direction. And if I'm slowing down, that means my acceleration is pointing upwards in a positive direction. So that means my net force must also be positive. So this case is very much like case 2, where I have a much greater net force or much greater normal force. So therefore the scale reading is going to be greater than my actual weight. And I'm going to feel heavier than I actually am. Now, what about free fall? So free fall means that my acceleration is negative g. I am accelerating downward according to gravity. So the acceleration is the acceleration due to gravity. So then my net force must equal my weight, right? Because net force equals mass times acceleration. So net force would equal mass times g. And therefore, mass times g, well, that's just the weight. So that means my net force is the weight. So I'm actually going to register a 0 scale reading. I'm going to register 0 newtons on the scale, which means I'm essentially weightless. If you